Hello, and welcome to the lecture on chapters 17 and 18. As you can see here, we're starting with chapter 17, but this lecture will also include in the later half chapter 18. The reason I'm including these two chapters together is because the topics are closely related. It's all about how chemicals react. It's the broad topic of chemical reactions. In fact, chapter 18, as you'll see in a few minutes, is specifically about two very important types of chemical reactions. But we'll lay the groundwork for understanding the general notion of chemical reactions here in chapter 17. But again, since those ideas are so closely related, we have one lecture for the two chapters. Furthermore, these chapters and this lecture will run a little long, both because it covers two chapters and because there actually is quite a bit of content. We'll talk about molarity and thinking about molecular weights and balancing chemical equations, which requires a little bit of analytical thinking. And we'll also introduce the pH scale, which is a logarithmic scale, which will require a little bit of practice with logarithms. So certainly there's this kind of mathematical side to these lectures, so you got to pay attention to those parts. But let's get to it. Okay, so starting off with the table of contents for chapter 17, the first half of this lecture. We're going to talk about chemical equations in general. We're going to talk about counting atoms and molecules by mass, okay? What mass? Atomic mass. What does that mean? That means referring to the periodic table and referring to the atomic mass of elements that are included in compounds, right, in molecules, okay? Then we'll talk about reaction rates a bit, how you can speed them up and slow them down, how catalysts affect those reaction rates, okay? What is a catalyst? Kind of a general idea of just about where to find them. You don't have to memorize the names of any catalysts or anything. Then we'll talk about energy and chemical reactions. In other words, chemical reactions that produce energy and chemical reactions that absorb energy. Okay, so certainly there's a numerical side of that, and we just got to make sure that we're clear on what it means to produce energy, what it means to absorb energy, because that can be a little tricky, but I think I'll be able to clear that up for you. And then we'll talk about how chemical reactions are driven by entropy, which takes us way back to the second law of thermodynamics. Because in fact, anytime you mention entropy, you're talking about the second law of thermodynamics. And what we're saying here is that chemical reactions follow that law, as they should, because nothing in chemistry says that physics is wrong. Therefore, physics should also explain parts of chemistry. And indeed, that's the case here. Okay, so refer back to the second law of thermodynamics in the chapter on thermodynamics. Okay, all right, so let's get into this content to introduce a chemical reaction. Now, obviously, we've been talking about chemistry for a few lectures now. We're just zooming in here on the specific side of the reactions, not the bonds. I assume you already remember some of the important bonds like covalent bonds, but instead how one chemical can become another chemical. Okay, that's the idea of this entire lecture covering both chapters. Okay, so to do that, we need to talk about something called a chemical equation. What is a chemical equation? Well, it's a lot like a mathematical equation, but there's no equal sign. Instead, it has an arrow linking the left and right hand sides of the equation. And what it means is that during a chemical reaction, one or more new compounds, which is to say new molecules, are formed as a result of the rearrangement of atoms. Okay? So we have the reactants, those are the input, and we have the products, which are the output. Okay? And all chemical equations are balanced. We'll come back to what that means. But here is an example showing some diatomic hydrogen reacting with diatomic oxygen and becoming water. Okay? That is an example of a balanced chemical equation, a balanced chemical process. All right? So, when we talk about chemical equations, probably the most important thing, which is why it's first, is that mass is conserved, which is the law of mass conservation. No atoms are gained or lost during any reaction, okay? This isn't high energy physics. This isn't atoms becoming pure energy. Atoms are definitely conserved in any chemical reaction, all right? Same number of atoms in as number of atoms out, okay? Also, the number of times atoms appear before the arrow must be equal to the number of times they appear after the arrow. In other words, oxygen can't become something else. There's no transmutation. An atom remains the same atom throughout the chemical reaction. That is a big premise, a big assumption of chemistry. No change in the atoms. In fact, the example here of our first balanced equation, we saw that we started with 4, because 2 times 2, 4 hydrogen total, and 2 oxygen. And how many do we have afterwards? The same number, right? If we look, we have 2 H2Os. Each H2O has 2 hydrogens for a total of 4, and then we obviously have our 2 oxygens. Okay, so same number of individual atoms on one side of the equation as on the other side. Okay, so in total, here's an example here in a check. How many atoms are represented by the following schematic for a chemical reaction? How many atoms are shown? Okay, because they're not named here, but we have some molecules becoming different molecules throughout this chemical reaction. All right, how many are shown? 6. The atoms of the reactants are the same atoms of the product, except in a different configuration. Whatever these black circles may be, whether they're carbons or oxygens or hydrogens or something else, the point is that there was 6 atoms to begin with, 6 atoms concluding, just arranged differently. Okay? And the process would probably look something like this. We'd start with the reactants, that's the input. They would break apart due to some chemical process, and we'll talk about what those chemical processes might be, including when we get into discussing bases and acids and oxidation and reduction, which is the content of chapter 18. But the point is that there's numerous different mechanisms all involving some flow of energy that can cause reactants to become the products. But here we're starting to see that in this kind of cartoonish pictorial way. Right, our atoms are splitting up from their original configuration. We have then moving off, actually changing their spatial configuration. They actually will always move relative to each other. And now they're regrouping to form these diatomic molecules instead of the original triatomic molecules, right? Instead of the original groups of 3. And now we're done, right? So that was just that's what would have happened to involve this chemical reaction, a balanced chemical reaction, because the number of atoms before and after are equal. Okay, all right. So in the conventional equation format, it would look like this, and all you see here are 6 different atoms. Okay. All right, so what about this example, right? Again, just a picture, right? Not using the conventional equation, but is this reaction balanced? Just looking at the picture here and acknowledging that the different colors must denote different types of atoms, right? Again, we don't care what they are. This is just kind of a general sense of what a chemical reaction looks like. But do you think it's balanced? Yes or no, right? No, definitely not. Why? Because some atoms disappear, right? These kind of pinkish red color atoms, they don't show up in the product. Where do they go? They can't become a new atom, so it doesn't make sense that they disappeared. This is not a balanced chemical reaction. Something was missing here. This was not a complete story, okay? And the number of atoms is also not equal from one side of the equation to the other. And again, the equations are always separated by an arrow, not an equal sign. Okay, what about this case? Right here, we're actually looking at a chemical equation like we saw way back when we looked at the oxygen and the hydrogen becoming H2O. So here's another good example of a typical chemical equation. But the question is it balanced? Okay, we'll take a look, right? So we've got, 1 CH4, we have 2 O2s, and it becomes 2 H2Os, so 2 waters, plus 1 CO2, 1 carbon dioxide, okay? All right, so which is it? And I think, yeah, and this one's methane over here. The CH4 is methane, okay? So is it balanced? No, because the molecules have changed. Yes, because the coefficients on either side add up to the same number. In other words, 1 plus 2 equals 2 plus 1. No, because there are more oxygen atoms in the products. Or yes, because the same atoms appear before and after. What's the correct answer? It's D, okay? Now, this is important here because saying it's balanced for the reason of B would be wrong, because yes, it is balanced, but not for this reason. The coefficients adding up doesn't necessarily mean a balanced equation. Instead, you have to ask yourself, how many total atoms are there? Well, in this case, there's a total of 2 times 2, or 4 O to start with, 4 oxygen. Are there 4 oxygen in with? Indeed, there are. Right, because we have 2 in the 2 water molecules, and then we've got another 2 in the single carbon dioxide molecule. But the point is that there's just as much oxygen in as out, and the same for carbon, all right, and hydrogen for that matter. Okay, so chemists need a way to mathematically express a chemical equation. The periodic table gives the formula mass of the elements, okay? So we've seen the periodic table before, which is good because it's worth seeing more than once. Now we're going to put it to use here in the context of these balanced chemical equations, okay? And a couple examples and a bit of review, because we have talked about the idea of a mole and Avogadro's number before, but it's okay if you don't remember, because you don't necessarily have to go back and rewatch it, because we're actually going to go over it again here, okay? So carbon, for example, has an atomic mass of 12, right? So one molecule, or in this case, one atom of carbon, has a mass of 12 AMU, all right? Atomic mass units, okay? Now, an AMU is a small amount of a kilogram, okay? It's about a 10 to the negative 27th kilogram, so one AMU is about 10 to the negative 27 kilograms, just to give you that real life context. It is an actual mass, it's a small amount of mass, but we won't refer to them as fractions of a kilogram. We're always going to use AMUs, okay? And the reason that they're approximate has to do with isotopes and the different numbers of potential neutrons that exist inside of the atomic nucleus. But again, that's kind of a review back to our chapter on nuclear physics, leading up to our discussion of chemistry and our unit on chemistry. But that's why there's always this decimal fraction, okay? It's the average of common isotopes that exist in nature. But we always round, okay? We always round to the number that's closest. And in this case, clearly 12 is the closest number for chemistry purposes. So we say that it has an atomic mass of 12 AMU. On the other hand, oxygen, which is further along the periodic table, therefore it has more protons, okay? Well, it also has more total nucleons, protons plus neutrons. And so it has, if it was a single oxygen atom, it has an atomic mass of 16, rounding up, clearly, right? 0.999 rounds up to 16, right? Or 15.999 rounds up to 16. However, oxygen, unlike carbon, really never comes by itself. It's always in a bond with another oxygen, and it becomes O2. And O2, which is the molecule we care about for practical purposes of chemistry, is always going to be two oxygens, therefore it's 16, which is of course just equal to 32, excuse me, which is of course equal to 2 times 16 AMU, because it's 2 oxygen, all right? It's O2. Okay, so a carbon atom is 12 over 32, or 3/8 as massive as an oxygen molecule. In other words, the oxygen is more massive in its molecular form, significantly more massive, okay? It's over twice as massive as a single carbon molecule, because carbon is just, it's atomic, it stays by itself, okay? Therefore, if you had a number of carbon atoms, an equal number of carbon atoms as a number of oxygen atoms, then which would be heavier? The oxygen, all right? If I had an equal number of oxygen, not atoms, but molecules, all O2, then it would weigh 8 grams. On the other hand, carbon would only weigh 3 grams because of that ratio, 3/8, okay? Now, to be clear, because we talked about it before, these are not 1 mole of each, because if it was 1 mole of carbon, it would actually weigh 12 grams. But obviously this is a fraction of a mole. In fact, we know exactly how much. It's 1/4 of a mole. We know it's 1/4 of a mole because we know that the number of grams in 1 mole is always just equal to the atomic mass numerically. So if you have an atomic mass of 12 AMU, then 1 mole would weigh 12 grams in the case of carbon, okay? And 1 mole is 1 Avogadro's number worth of individual atoms or molecules, okay? Depending on if the compound exists in an atomic state or a molecular state. Okay, we'll review what Avogadro's number is in just a second. Let's go on the next slide. So Avogadro's number relates the mass to the number of molecules. Okay, so Avogadro's number, right, has to do with a mole. That's why we have this picture of a mole, just as a reminder that Avogadro's number, tied with moles, it is this many atoms. It's that many atoms per mole. 6.02 times 10 to the 23 atoms per mole. A lot of atoms, huge number, okay? So for example then, sodium has an atomic mass of 22.9, right? Which we can round up to 23 in many purposes, or we could just say that 22.99 grams is the weight of 1 mole of sodium, right? And this is sodium in the solid state as a rock. On the other hand, we have Pb here, which is our I want to say iron. I'm drawing a blank on it, but it's a much larger atomic nucleus, a lot more protons and neutrons, with a total atomic mass per atom of 207 AMU, which means 1 mole is 270 grams. Likewise, helium, quite light, a light gas, the second lightest gas out there. The only thing lighter than helium is hydrogen. Well, the atomic mass of helium is just 4 AMU. Therefore, 1 gram of helium just weighs, 1 mole of helium weighs just 4 grams. Okay? So heavier elements have heavier weights per mole. Okay? Always measured in grams, by the way. Okay? Now, physicists tend to stick to only using kilograms. Chemists here are really committed to using grams for the definition of a mole. Okay. So going back to the idea of chemical equations and balancing those chemical equations, we can consider how many moles go in to how many moles go out. And this part is interesting because it's not like every part of the chemical equation has to have the same number of moles. You have to think about how they combine with each other and what the ratio of the input molecules are to the output molecules. And if that statement sounds a little confusing, I would totally understand why, but we'll see it put into practice in the next few examples. Okay? So let's take a look at this chemical equation. We've got 2 moles of diatomic hydrogen and 1 mole of diatomic oxygen. All right? The weight of the 2 moles of diatomic hydrogen is 4 grams. Okay? And the total number of molecules is just 2 Avogadro's number worth of molecules, which is 12 times 10 to the 23 molecules. All right? So about 1.2 trillion molecules. Okay? Now, 1 mole, of course, is just 1 Avogadro number's worth, and that has a weight of 32 grams, just based on the atomic mass of oxygen. All right? And then this chemical reaction leads to 2 moles of water. Now, 2 moles of water is this many molecules, and the weight is 36. The reason it's 36 is because the mass was conserved. 4 grams plus 36 grams equals 36. Also, the reason it's 36, right, because there's more than one way to look at something, is because that is the atomic mass of 2 H2O molecules would be, well, 18 AMU per H2O. If you have 2 of them, 18 plus 18, you've got yourself 36, okay? And again, and that 18 is just coming from the 16 for the oxygen plus the 2 for the 2 hydrogens, because each hydrogen has an atomic mass of just 1 AMU, because it's just a single proton. Every nucleon has a weight of 1 atomic mass unit, okay? Okay, so you might ask yourself, though, how did we have 2 plus 1 equal 2, if we're just looking at the moles? Because that part can be a little jarring. Well, it's how things are combined. Because we had to combine, well, look, you had 1 mole of the diatomic oxygen, but you only needed that 1 mole because look what went into it, right? You only had to put 1 hydrogen in to each H2O, whereas you had to put 1 oxygen into each H2O, whereas you had to put 2 hydrogen into each H2O. Therefore, the ratio of hydrogen to, inputting hydrogen to outputting H2O, outputting water, was the same. But the ratio of oxygen, we didn't need as much oxygen because you only needed half of that O2 to get each H2O. That's why you only needed 1 mole of the oxygen, because of the actual distribution or ratio of oxygen to hydrogen in the final product. Okay, so it's completely correct to say that 2 moles of H2 plus 1 mole of O2 equals 2 moles of H2O. Okay, so that's what I mean by the ratios of the inputs to the outputs, the ratio of the reactants to the product. Okay, so let's do some checks here. These are numerically based. How many moles are in 45.5 grams of chlorine gas? Now you can answer this question, but you need to look up the periodic table. So let me give you a hint. First, I'm going to show you the actual form from the periodic table for chlorine, right? Well, chlorine has an atomic number of 17, which we haven't talked about too much. That's just the total number of protons. That's its place on the periodic table. But what we care about here is its atomic mass, which is about 35.5. Okay. All right, and that's just the sum average weight of how many protons and neutrons there are in the nucleus. Okay. So, therefore, if I have 45.5 grams of chlorine, then how many moles is that? Well, another hint is that chlorine is diatomic. A lot of things are, right? Oxygen, hydrogen, not everything. Carbon wasn't, but chlorine is diatomic. So that means that chlorine would never be by itself. It would always be Cl2. Well, if 1 chlorine has an atomic mass of 35, what's the atomic mass of Cl2, of 2 chlorine together? Well, it's going to be about 70, all right? So 70 AMU for Cl2, okay? Well, if it's 70 AMU per molecule, then what is it per mole? Well, 70 grams, right? 70 grams per mole. And we were told that we have 45.5 of those. Well, what's that closest to, right? Well, now you should be able to figure this out. Get out a calculator if you need to. It's closest to 0.64 because we would just take that 71, right, or 70, round to 71, right, and just find out how much, what fraction 45.5 is of 71, and it's 0.64, which is how many moles there are in that many grams of chlorine gas, a diatomic gas formed out of chlorine with this particular atomic mass. Okay? So that's how you piece together the information to answer a question like this. Okay, let's do another one. How many grams of water are produced from 1.25 moles of methane? Okay, so here's the methane. Here is the diatomic oxygen. Here's the product of the water and the other product, which is the carbon dioxide. Okay, so one thing to consider is the actual atomic mass of water. All right, and here I'm showing you how you would come up with that value. So for one H2O molecule, well, that involves two H. Each H is about 1, right? So you have 2 of those. And then you're adding 16. So 16 plus 2 is 18, which I mentioned before. But here you can actually see how you come up with that number. That's the number of grams per mole for water. So in other words, 1 mole of water weighs 18 grams, okay? Or 18.02 grams. Great. Okay. But we were asked how many are produced from 1.25 moles of methane. Well, let's look here. We have methane coming in, right? And we have water coming out. Is the ratio the same? Are we getting just as much water per methane? No. We have, for every 1 mole of methane, we're getting 2 moles of water. How do I know that? From the coefficients here, okay? So if I put in 1.25 moles of methane, how many moles of water should I get? Okay, well, I should get 2, all right? And what should the weight be? Well, the weight should just be 2 times this number, all right? So that's going to give us our that's going to give us our 45 grams, okay? Because we didn't have exactly 2, we started with 1.25, so 1.25 times 2 gives us 2.5, and then we simply multiply 2.5 times the 18 that you saw right here. 2.5 times 18 is 45. Okay, so what did you need to answer this question? You needed the ratio, the fact that you're getting 2 moles of H2O for every 1 mole of methane. Okay, that allowed you to find out how many total moles of water there'd be, and you needed the actual molar weight, how many grams each mole weighs for water. Once you had that, you were able to answer the question. Okay, so you just clearly need to figure out how to find those information and do those steps. Okay, let's do one more. How many moles of carbon dioxide are produced from 50 grams of methane? Okay, so again, we have the same balanced chemical equation with our methane and oxygen becoming water and carbon dioxide. But in this case, we're focusing on the carbon dioxide, and we're given different information. We're given how much methane we start with, 50 grams of methane. Okay, so let's think about that. If I have 50 grams of methane, then and I'm forming carbon dioxide, I need to know the actual atomic mass of the carbon dioxide, okay? So I look over here at the carbon dioxide, and we've talked about oxygen already, having the atomic mass of 16, and we know that carbon has an atomic mass, based on the figure here, or looking up in the periodic table, of 12. Okay, so then I have 12 plus 2 times 16, and that's going to give me the atomic mass, or molar mass in grams, of carbon dioxide, okay? So 32, and then we have, 34, 44, okay? So 44 grams per mole for CO2, okay? And we had 50 grams going in. Well, here's the good thing. If we have 50 grams going in of the methane, and we've got, this much carbon dioxide coming out, which we know has a molar weight of 44 grams per mole, what about the ratio? Because that was something I had to consider in the last example. Well, the good thing that I just started saying a minute ago is that here our ratio is exactly 1 to 1. All right, so we have just as much carbon dioxide coming out as methane. So we don't have to worry about doubling anything. We just say, okay, well, for every 50 grams of methane, we should get an equivalent amount of carbon dioxide, right, of carbon dioxide. Well, but we won't get 50 grams of carbon dioxide because carbon dioxide has a different molecular weight, right? It's got a different different number of grams per mole. So how much will we get? Well, right, so we start with the 50 grams of methane, right? And we know it's a 1-to-1 ratio. So therefore we can say, okay, well, converting the number of grams, knowing that 1 mole of methane is 16 grams, then we can come up, right, because this one here, the methane has, and I guess we care more, right, I started talking about the atomic mass of CO2, excuse me for that. We really should focus just on the atomic mass of the methane. And let me show you why. Well, here we take carbon, which we know has 12, all right? And then each hydrogen is 1, so that's plus 4 times 1. That's going to give us the 16. Well, if there's 16 grams per mole for methane, well, then how many moles is this? Well, if there was 50 grams of it, then I simply take 15 and divide by 16. So 15 divided by 16 gives me 3.13 moles. And then that 1-to-1 ratio says that there must be the exact same number of moles, since it's 1-to-1, of carbon dioxide, right? Now, if I was asked for the actual weight of the carbon dioxide in grams, then I would need to consider this number, the 44 grams per mole. But as the question was asked, that was a tangent, an unnecessary one, because we're done. Once we have that 3.13 and the 1-to-1 ratio, we know that that is exactly how many moles of carbon dioxide are produced. Okay, good. So these last 3 examples, definitely a little involved. They all have more than one step to them, but they really illustrate what it means to have these balanced chemical equations and consider molecular weight, which is just grams per mole. Okay, all right, so with that out of the way, let's talk a bit about reaction rates. So reaction rates are the speed with which products form from the reactants. So like all the previous reactions we've been talking about, the chemical equations, all of those are reactions and they all happen at some rate. They don't happen instantaneous. It does take time, usually just fractions of a second, but certainly it takes time. And that rate is affected by concentration, temperature, and something known as a catalyst, which we'll define in just a moment. Now, the premise behind the reaction rate being affected by these criteria is that the molecules have to make physical contact. Right now, of course, there's trillions upon trillions of them, so we don't, typically zoom in on the individual interactions between atoms or molecules. We consider it as a overall probabilistic effect, but ultimately, at the submicroscopic scale, there are these molecules bumping into each other. All right, and that will allow for the transformation. So if we kind of take a picture of that, we can consider a less concentrated mix of some molecules, right, in some diatomic form here, and specifically N2 and O2. So the N2 are the blue ones and the O2 are the red ones. We typically represent oxygen as red, okay? And so we're bumping them together. If there's more of them, if they're more concentrated, there's more chances, a greater likelihood for collisions. And then those collisions have sufficient energy to change the chemical bonds and create a new chemical. In this case, nitrogen monoxide, with an example shown here, which presumably followed some collision, okay? So that's the idea, is that more concentrated means more collisions, thus a higher reaction rate, okay? More products being created per second. Also, temperature matters, because even if the concentration is high, or especially if it's low, when the molecules come together, they might come together very slowly, and when they bounce together, they actually don't have enough energy to react. So they bounce off of each other, they ricochet off of each other in their intact original chemical compositions with no actual chemical reaction taking place. No need to balance because nothing happened, right? Because they just didn't have enough energy to break the bonds that held together these diatomic nitrogen and oxygen, right? Because they definitely had, they had those covalent bonds. And in this case, there just wasn't enough energy to break those bonds and form a new bond, okay? All right, and we'll come to that idea of breaking bonds and forming new bonds in just a second, and the whole premise of energy. But here, obviously, very low temperature, very slow motion, there might be no reaction at all, or at least less likely reactions, which means a slower reaction rate. So if temperature goes up, reaction rate goes up. Temperature goes down, reaction rate goes down. And a catalyst. Well, what is a catalyst? Well, to understand a catalyst, we have to understand that there is a certain energy necessary to break the original bonds. Because you start with the reactants, in this case, diatomic nitrogen and diatomic oxygen. In order to split them apart and form the product of nitrogen monoxide, and specifically an equal number of nitrogen monoxide to make a balanced equation, we need to split the diatomic bonds and then allow new bonds to form. But splitting those bonds takes energy. There's a minimal amount of energy necessary, right? You can think of it as an energy hump that has to be overcome. The reason that the energy hump peaks out and then drops back down is because when the new bonds are formed, energy is released, okay? So that's why it drops back down. But regardless, you can't get back to this plateau where the new bonds have been formed and energy has been released without overcoming the hill in the first place. That's the necessary energy for the reaction to take place. Okay? All right. So breaking the bond takes energy, even though reforming the bond releases energy. Okay. Well, that's the energy required for the reaction that takes place. That is the reaction energy or the activation energy. Okay. Well, can you affect that activation energy? Certainly, by having a catalyst. A catalyst changes the necessary energy. A catalyst allows for a process that instead of looking like this, the example here being ozone becoming oxygen, all right? So O3 becoming O2, instead we have some intermediate step and an overall energy threshold or activation energy that's reduced. So a catalyst has the effect of lowering the activation energy, which allows the reaction to proceed at a quicker rate. So on the basic level, that's the definition of a catalyst. Is it just lowers the activation energy. It makes there's a easier breaking of bonds. Therefore, reactions can happen more easily. Therefore, they happen more quickly. The reaction rate goes up. But to dive in a little bit more to what a catalyst is doing, a catalyst always creates an intermediate step, which is hinted at in this diagram because we have this extra little dip in the middle. Well, that extra dip represents the actual extra chemical process. So that means instead of just having a single chemical reaction, ozone to O2, we instead have ozone to something else, then reforming, and then maybe a third final chemical reaction, as is shown here. So carefully examine the following reaction sequence of the catalytic formation of ozone from oxygen. So this is actually going the other way. This is forming ozone from oxygen, which is also plenty possible. The reaction is going to go either way. In this case, we have a catalyst, right? Well, what is it? Well, here's our first balanced chemical equation, followed by a second balanced chemical equation, and a final third balanced chemical equation. The idea here is that these three reactions lead to the final product of ozone, starting with oxygen. Okay, but what was the catalyst? What allowed for this to happen at a lower threshold energy? And we're not giving the values of energy, just looking at this information, can you determine what must be the catalyst? Is it nitrogen dioxide? Is it nitrogen monoxide? Is it atomic oxygen? Or is it oxygen itself? Which one is the catalyst? All right, this takes a bit of interpretation, but if you have a good guess, commit it to your mind. Let's see the answer. It's the nitrogen monoxide. It's the NO. Why do we know that? Well, we know because it forms with the O2 in order to form O3. In other words, the nitrogen oxide gets this reaction going in the first place. As another clue, note how the nitrogen monoxide is regenerated after the second reaction, which means it'd be available again to keep the reaction going, which is a sign of a good catalyst. Okay, and that's as far as we need to understand catalysts, their definition, and that they require some intermediate step, which lowers the overall activation energy required for from the beginning to the end, right? From in this case, starting with oxygen, ending with ozone. Okay, all right. So let's get on to a different topic, still here within chapter 17, and that's the understanding of which chemical reactions release energy and which ones actually require a continual input of energy. And those two different cases are represented by the keywords exothermic reactions and endothermic reactions. Well, what is an exothermic reaction? Well, it's a chemical reaction that actually results in a net product of energy. So energy is released, okay? So we have reactants to products, some balanced chemical equation, and an excess of energy. On the other hand, an endothermic reaction is a chemical reaction in which there is a net consumption of energy. So that means that the reaction plus the products there's not enough energy for it to happen spontaneously, and we'll come back to the idea. So instead, we have to have energy to start with in order for the reaction to even take place at all. All right. So there has to be energy to begin with, excess energy, because it will get consumed within the reaction. Okay. So to understand the actual values of this, we can actually think about the bond energy in certain covalent bonds. Covalent bonds being such an important type of chemical bond. And again, there are other types, ionic bonds and so on, but covalent bonds are so crucial to most of these really common chemical reactions. So for example, diatomic hydrogen, here we have hydrogen carbonate, hydrogen carbonide, right? Here we have hydrogen nitride, lots of different molecules, small molecules, because we're just sort of illustrating a point here. And we're looking at the bond energy of these different molecules. And the energy here is represented as kilojoules per mole, right? A mole just being, exactly one Avogadro's number, so what, six times 10 to the 23 atoms worth of this molecule, right? So the bond energy, for example, of diatomic hydrogen is 436 kilojoules, and kilo just means, so it would be 10 to the 3 joules per mole, all right? So kilo means 1,000, all right? So that's how much energy there is for 1 mole of this substance, holding together all those diatomic hydrogen atoms, okay? And you can look at all the different molecules, and they have different binding energy. It varies, right? It just depends on the particular characteristics, and of course, if we're zooming on the atom, where those electrons are within the different shells of the atomic model, all right? And obviously, as we get to stronger covalent bonds, like double covalent bonds, and even triple covalent bonds, the energy significantly goes up, as you might expect, okay? All right, but even within double bonds, some of them are actually fairly low, like diatomic oxygen, but certainly the double covalent bond between carbon and oxygen is pretty high at 803. Okay, but point being, we got variation between the bonds. This is really a testament to how some reactions are going to require energy input, and some are just going to produce energy because of all these variations in the binding energy. So let's do one particular case, all right? Let's use the bond energies below, which are listed here in this blue box, to determine whether the following reaction is exothermic, meaning it releases energy, or endothermic, meaning it consumes energy. Okay, so let's consider the bond energy of diatomic hydrogen, 436 kilojoules per mole, diatomic chlorine, so that chlorine gas, 243 kilojoules per mole, or hydrogen chloride at 431 kilojoules per mole. Okay, so which is it? Is this reaction exothermic, endothermic, right? And why, right? Or with more detail. Is it exothermic with more than 50 kilojoules of energy released? Is it endothermic with more than 50 kilojoules of energy absorbed? Is it endothermic with less than 50 kilojoules of energy absorbed? Or exothermic with less than 50 kilojoules of energy released? And this means we have to actually check the numbers, because we can't just, it's not enough just to identify which is bigger. We have to find out how much it's bigger so we can correctly distinguish between B and C or A and D, okay? So run the numbers for yourself, all right? Or just stay tuned, because I'm going to explain how to answer this. Okay, so the correct answer is it's exothermic with more than 50 kilojoules of energy released. So there's quite a bit of energy released. How do we know that? Well, let's consider the bond energy. So the bond energy for the diatomic hydrogen was 436. The bond energy for the diatomic chlorine gas was 243. Now, the hydrogen chloride, there was 2 of them, all right? So it ended up being 431 per hydrogen chloride. Okay, well, if you look at that, you might say, well, actually this number is small. The 431 is smaller than some of these other 2 numbers, so it seems like there's less energy on the right-hand side. But that's not the right way to think about it. Instead, think about it this way, all right? You would take this total value, right, the sum of the binding energy to start with, that's how much energy is absorbed. That's how much energy it takes to break the bonds, because it takes energy to break bonds, all right? So requires energy to break bonds, okay? And that's what you're doing on the left-hand side of the equation. You're breaking bonds every time, okay? Now, if something was just a pure element, it was just a single, like just H on its own, or just, carbon on its own, then there's no bond to break. But anytime you have a molecule, then there is a bond to break, okay? So that took energy, so it absorbed 679. But then on the other side, we had the hydrogen chloride, and we had 2 of them. So we take the 431 and we multiply by 2, which gives us our 862. And again, just 2 because of the balancing of the equation. And we have to have just as much hydrogen and chloride on either side, right? Or chlorine on either side. Okay, but rebuilding bonds is a release of energy, all right? Releases energy. Now you might think, wait, why does building a bond release energy, whereas breaking a bond requires energy? Because it's all about potential energy. These things, they want to be pulled together. When you let them be pulled together, it's like dropping something down a well. You're allowing the energy to get released. You're allowing the potential energy to become the binding energy, okay? And that's why it's a release of energy to let them come together. So anytime a bond is created, that is a release of energy, okay? And indeed, then we see that since there was 862 released, but only 679 absorbed, then there was a net change of 183 kilojoules per mole. That's how much was released, which is more than 50 kilojoules of mole, or 50 kilojoules of energy per mole. Therefore, it is number A. It's exothermic with quite a bit of energy per mole. All right, good. So it is the natural tendency of energy to disperse from where it is concentrated to where it is dilute. Again, that's the second law, of thermodynamics, which I'll just shorthand as thermo, okay? So that's just a restatement. We've seen that before, but it applies really well here to this idea. That means that something like a hot pan radiating heat definitely follows this idea, right? Gasoline combustion into smaller molecules, right? Marbles bouncing on the floor coming to a stop, right? So this, these energies changing form, because what's happening is entropy is increasing in each state. More ordered energy is becoming less ordered energy. Heat being less ordered than, say, like, potential energy of something up on the top of a ramp or a marble in your hand. Okay? It is the term used to describe the degree to which energy has become dispersed, so less organized. Okay? So the reactions that result in an increase in entropy tend to occur on their own. They'll happen spontaneously. Again, second law of thermodynamics. Heat will spontaneously flow from hot to cold, but not the other way. Things will spontaneously become more entropic, more disorganized, but not the other way. Things don't spontaneously become more organized. Okay, that means that one of these types of reactions leads to a greater dispersal of energy and can happen spontaneously. Which do you think it is? All right, it's exothermic. Any reaction that just releases energy spontaneously will happen spontaneously. Okay, exothermic reactions can happen on their own. Okay, so exothermic reactions tend to be self-sustaining, all right, spontaneous, because they lead to a large increase in entropy following the second law of thermodynamics. Therefore, a campfire is self-sustaining. Endothermic reactions, on the other hand, require a continual input of energy. They don't just happen on their own. Photosynthesis will only happen if the sunlight is there. It won't happen on its own. Okay? All right, so finally on to two other big types of chemical reactions. So continuing on the topic of chemical reactions, but specifically talking about acid-base reactions and oxidation-reduction reactions. Now, some of this I won't go into so much detail because I do want you to just think of this as two other types of chemical reactions. The fact that I've combined chapter 18 here with chapter 17, and ignore this should say 18 up here. But the fact that I've combined these two chapters is really meant to tune you into the fact that the content in chapter 18, don't think of it as so much a standalone chapter. Think of it as just further cases, further illustrated examples of the content from chapter 17. It's meant to sort of lower the stress of having to learn everything in chapter 18, okay? Again, all right. So, some key ideas we want to understand. The definitions of acids and bases, in that acids donate protons and bases accept them. All right, so we definitely want to get that out of the way, try to memorize that. We want to understand the relative strengths of acid and bases. We also want to talk about acidic, basic, and neutral solutions, all right, which is going to take us into pH and the pH scale. That's going to be our little aside talking about logarithms. Then we'll talk about some consequences of the pH scale in terms of acidic rain and basic oceans. Then we're going to get into oxidation reduction reactions, which is the losing and gaining of electrons. And we'll compare the two because there's going to be a good way to sort of memorize why these two reactions are so fundamental and so important, but we'll come back to that. Then we'll talk about harnessing the energy of flowing electrons, since losing and gaining electrons then leads to kind of that idea of energy flow and how you can get something like a chemical battery to create a current. We'll talk about electrolysis and corrosion combustion, but just briefly. Okay. All right, so let's talk about acids and bases. Maybe you recognize that some of these are acidic and some are basic. All right. All right, here are some examples. All right. So by the way, these ones are all acids, including vinegar and citric acid. All right, and the and sodas like or at least colas, and these are all bases like Drano and soap and baking soda. Okay, so an acid, simply put, is a chemical that donates a hydrogen ion. Okay, right, so we talked about ions before. If you don't remember at all what an ion is, I'd highly recommend you go back and look at the chapter where we introduced ions, but hopefully you remember what they are. And a base is a chemical that accepts a hydrogen ion. So we got donates and accepts, so gives up and absorbs. Okay, so acids donate, bases accept. So here's a hydrogen atom, right? Simplest atom in nature, in the universe. A single proton and a single electron, right? Just one proton and one electron. Positively charged proton, negatively charged electron. They're attracted to each other. Quantum mechanics explains why they don't just crash into each other. Okay, great. Fundamental building block of the universe. But sometimes this hydrogen atom loses its single electron, all right? Because of some energy source causes electron to get excited to higher energy states, which are outer shells, which are completely unoccupied because there's no other electrons. And as that hydrogen atom continues to get a more and more excited electron due to some input of energy, even something like friction energy or heat energy coming into this atom. Eventually, the electron gets so far away that it can no longer feel in any significant way the Coulomb force, the electric attraction to the nucleus, to the proton. And so what you're left with, once the electron is gone, it's just out of the picture now, now you don't have a hydrogen atom anymore. So you used to have an atom, now you have an ion. Because an ion either has a net negative charge or a net positive charge. And in this case, without any electron at all, clearly the charge is positive. It's just a single proton. See? All right, that's the hydrogen atom. And if we kind of zoom out and consider the hydrogen ion, as it interacts with other compounds, other molecules, we can recognize that H plus is literally just a single proton. So saying a hydrogen ion is just code or alternative wording for a proton. So when we talk about acids and bases, we're talking about exchanging of just single protons. Okay? All right. It is a proton. A hydrogen ion is none other than a proton. Okay, so a good mnemonic device, a way to memorize this, is that we can remember BAD, right? Because bases accept and acids donate. Okay, BAD. Well, let's look at an example, right? So we've got hydrogen chloride and we've got water. Well, which one is the base and which one's the acid? Well, if you've heard of hydrogen chloride, you probably know it's an acid, but so then maybe you can see it happen, right? What's going to happen is the hydrogen chloride is, so a mnemonic device, right? It should donate, right? The acid should donate. Is that what's going to happen? Absolutely. See, the hydrogen chloride donates this single proton, because that's what this is, right? This is hydrogen. But once it gets given to the H2O, it's effectively a proton because it's just giving the proton, not the electron. The electron is staying behind in the chlorine. So now the chlorine has an excess electron. It's got one extra, which means now it is an ion with a net negative charge. And our hydronium, which is the name here, which we'll come back to, hydronium, of H3O is a positive ion because it has a missing electron. Okay, it has one less electron than it would need to be neutral. So it has a net positive charge. Okay, so here we had an acid-base reaction of the acid hydrogen chloride giving up a single proton, a single hydrogen ion. Okay, all right, here's the overall effect. All right, giving it up. So we see then that the donor was the hydrogen chloride, the acceptor was H2O. Therefore, the hydrogen chloride was the acid and the water was the base. Very good. Okay, let's look at a totally different example. Let's look at water and nitrogen trihydroxide. Not sure on the name there. But point being is that it's actually not completely different because it actually still has water in it, right? Last one had water as one of the original reactants. So does this one, okay? So what's going to happen in this case? Well, the water has got to be the base again, right? Not so. In this case, the water is going to play the role of the acid, okay? The water is going to give up a hydrogen, specifically a hydrogen ion, which means it's going to leave an excess electron behind. We'll draw it there so you can see it. So an excess electron is left behind we have our hydroxide, right? That's the name of OH. This is a hydroxide ion, right? The other one, by the way, was a hydronium ion. And then we end up with this positive ion over here. So interestingly, we see that water can, in this case, play the role of the donor. The NH3 plays the role of the acceptor. And we see then that water is being the acid, where the NH3 is being the base. So water can be both. It can be both the acid or the base, depending on what it's reacting with. Okay, well, then the reaction could go the other way, right? We could have these ions become neutral, right? And in this case, the water again, well, I should say the hydroxide ion is playing the role of the base, okay? And then our acid is the NH4 plus, and then our product is going to be the water, right? If we're going this way here. But the point is that this reaction could go either way depending on what you start with. Okay, so when water behaves, because we've seen it does both, as an acid, what does it lose? Okay, so this is just review, making sure that these terms are sinking in. Does it lose a hydrogen ion? Does it lose a hydrogen atom? Does it lose an electron? Or can water not behave as an acid? Well, it loses a hydrogen ion. As an acid, it's the donor. Okay, all right, okay. Acids donate, bad. Bases accept, acids donate. When water behaves as a base, what does it gain? A hydrogen ion, a hydrogen atom, an electron, or can it not behave as a base? Well, I bet you know the answer. It gains a hydrogen ion. So in both cases, it's all about hydrogen ions. Acid-base reactions are all about exchanging hydrogen ions. Good, which is to say they're all about exchanging protons. All right, so which water molecule is behaving as an acid and which is behaving as a base? Okay, so here we're looking at two water molecules, molecule A and molecule B, which is behaving as an acid and which is a base, which is donating and which is accepting. All right, so hopefully you can see. Okay, all right, molecule B as an acid, molecule A as a base. And here we're getting our hydronium ion and our hydroxide ion as the products of the reaction. Okay, so that's interesting because that tells us that just neutral water, two neutral H2O molecules can become ions of hydronium and hydroxide. Will that happen spontaneously? Yes, okay? Especially, maybe not spontaneously is the right word because in this case, the reaction would require an input of energy, but there's always some ambient energy. We're talking about liquid water after all. You know, it's at some temperature above absolute zero, and that energy coming in causes these reactions to happen. And that means that in any population of water, there's always going to be some hydronium ions and some hydroxide ions. Interesting, okay? This is just showing how it happens, right? So, you know, you have your two neutral atoms, eventually molecules, excuse me. One of the molecules is going to get to a point where the hydrogen ion breaks off, and then it'll get pulled in and attracted to the neutral H2O, and specifically because it's polarized, right? It's getting attracted to its negative end because remember all H2O molecules are polarized. They are all have a positive end and a negative end. So in this case, the positive proton gets attracted to the negative end of the molecule, thus forming the hydronium. Okay. Also, salts are important in understanding acid and bases because often if you mix an acid and a base, you get a neutral salt. It is or rather you get an ionized salt. It is an ionic compound formed from the reaction of an acid and a base. And really, let me stress that, it's the salt is formed in an ionic form. It's not formed neutral, but we'll see that in the chemical equations coming right up. And salt here is a general term. This isn't strictly table salt. Table salt is an example that's formed through an acid-base example, but there are other types of salts. Okay, here are quite a few of them. Here we have an acid and a base, right? For example, hydrogen cyanide mixing with sodium hydroxide to form sodium cyanide plus water. Okay, sodium cyanide, not the type of salt you want to be eating, but definitely a type of salt. Okay, and we have lots of other examples of acid bases mixing together to make salts. So everything in this column is a salt. Sodium cyanide, potassium nitrate, calcium chloride, and sodium fluoride. All examples of salt, because that's a general term. It's really a general term referring to the product of these acid-base reactions. Notice that there's always this byproduct or secondary product of water, usually 1 mole worth or sometimes 2. Okay? Here's another example. Here we have pseudoephedrine, a base, mixing with the acid hydrogen chloride to form pseudoephedrine hydrochloride, which is a salt. Okay, so what salt forms from the reaction of hydrogen chloride, HCl, with potassium hydroxide, KOH? What's going to form? Just based on what you know about these chemical equations, what must form? There's only one answer of our options of A, B, C, and D that makes sense. See if you can answer this, because this is the level that you need to understand the chemical equation side of acid-base reactions. Just being able to, you don't need to memorize the particular salts or anything, certainly not pseudoephedrine hydrochloride. You just need to understand the trend here. So what is it? It's the calcium chloride, right? Because the K plus from the KOH combines with the chlorine ion to form hydrogen chloride, right? And because if you think about it, of course it does, because you've got the other products are just going to form H2O, the remaining values from the original acid and base. And we saw that in those salt reactions, it was always H2O that was left over, right? So we kind of just, maybe one way to think about this is just subtract the H2O, and what are you left with? The KCl. That's why the answer must be A. Okay, so hopefully that makes sense, because that's the level that you need to understand, as I said, these chemical reactions of acid-base. Okay, furthermore, strong acids and bases ionize completely in water. A strong acid, such as hydrogen chloride, is going to just turn into chlorine ions and hydronium, right? So there's nothing left of the original acid. On the other hand, a weak acid and a base does not ionize completely in water. So if you take, for example, acetic acid, a much weaker base, or much weaker acid, excuse me, it's definitely not base, a much weaker acid than hydrogen chloride, well, you're still going to have a acid left behind, an acetate ion, so it doesn't completely dissolve, in other words. Okay? And as we said before, water, and it really illustrated, water can behave as an acid or a base, which is pretty neat about water. Not necessarily unique to water, but certainly interesting about water. Right? So water plus water can then form a hydroxide ion and a hydronium ion. And I mentioned these terms, but this is an important slide because it really clearly labels these two common ions. Okay? So in pure water, for every one hydronium ion formed, there's always a hydroxide ion. Okay? There always has to be an equal amount of hydronium and hydroxide. In fact, the fact that they're equal amounts is great because it means they're balanced, okay? And that's going to take us to the pH scale and that idea of having a neutral pH. But what's also interesting is their actual concentration to H2O. Because what we have here is that there is 10 to the negative 7 M. What is M here? This is molar concentration. So that means that for every 10 to the 7 atoms of H2O, there's exactly one atom of hydronium and one atom of hydroxide, both ions, right? So one ion of hydronium, one ion of hydroxide for every 10 million neutral H2Os, all right? That's what that molar concentration means, because 10 to the negative 7 is 1/10,000,000th, okay? Well, that 7, that's going to then be applied to the pH scale, because 7 is neutral pH. Okay, if you've seen that before, if you've seen that term 7 pH, this is where it comes from. It comes from molar concentration, that 1 in 10 to the 7. Okay, all right. So in a neutral solution, equal number of hydronium to hydroxide, we have a pH of 7. Okay, we'll come back to the mathematical definition, but for now, do note that that 7 is absolutely connected to that 7. Okay, and this just shows here that they're balanced. So if you put them on a scale, there'd be, they exactly balance out in terms of how many there are. Okay, so if you add hydronium ions, then the solution becomes more acidic. If you add hydroxide ions, the solution becomes basic. Okay. All right, so therefore we could think of an acidic solution of having an excess of hydronium, and we can think of a basic solution having an excess of hydroxide. Okay, excellent. So as sodium hydroxide, NaOH, is added to water, the hydroxide ion, OH, concentration should do what? Should it increase, decrease, or remain the same? Well, it's going to increase because the bond between the sodium and the oxygen is ionic, which dissolves in water, as all ionic bonds dissolve in water due to the polarized nature of the water molecules. And then it separates into sodium ions and, hydroxide ions. So that means adding a salt actually makes the water more, well, OH negative, which is to say it becomes more basic. So adding this particular salt makes the water more basic. Okay? So pH, which I've hinted at, now we're going to kind of formally introduce it, is a measure of the concentration of hydronium ions. Okay, so it's a scale that measures how much hydronium there is. So a higher pH means more hydronium. A higher pH means more basic. Okay, so pH is the negative of the log of the concentration of H3O+. So remember that for pure water, there was exactly 1 in every 10 million of these. So there was one of these ions for every 10 million neutral H2O molecules. So that meant that there was a negative log of 10 to the negative 7. That was, again, was the molar concentration. Okay? Well, if you follow the mathematical rules of logs, then a log of a power of 10 cancels out, and then we're just left with negative times negative 7. The negatives cancel, and then we're just left with 7. Okay, so pure water has a pH of 7. Now, if you're asking yourself what the heck is a log, let's quickly review. All right, so the log of a number is simply the power to which 10 is raised. So in other words, the log of 10 to the 3 is just 3 because it's raised to the power of 3. So log of 10 to the 3 is 3. But we'll see that a couple more times, okay? So what is the log of 10 raised to the second power? Okay, well, that would be the log of 10 to the 2. It's just 2 because 10 was raised to the power of 2. So asking for the answer of log of 10 to the 2, it's got to be the power. It's just 2. Okay? Now, we can also numerically represent them. So 10 to the 3 is 3 zeros, so it's 1,000. Okay? So 10 to the 2 is 2 zeros, so it's 100. 10 to the 1 is 1 zero, so it's 10. We can also have negative powers, negative exponents. We saw it with the negative 7. So 10 to the negative 1 is 0.1. All right? Because that's like 1 over 10. 10 to the negative 2 is 0.01, because that's 1 over 10 squared, which is the same as 1 over 100. So it's 1/100th, okay? And then 10 to the negative 3 is 1,000th, because it's just 1 over 10 to the 3, all right? So 10 to the negative 3 is the same as 10 to the 3 in the denominator, okay? That's kind of a rule of exponents. But notice we left off the middle, which would be 10 to the 0. What the heck is that? What's 10 to the 0? Well, if 10 to the 3 is 3 zeros, 10 to the 2 is 2 zeros, and 10 to the 1 is 1 zero, then 10 to the 0 should be 0 zeros. It's just 1. So 10 to the 0 is 1, and that works mathematically. Okay, that's a rule of mathematics, and it's completely consistent with the rest of mathematics. Okay, all right, so quick quiz. What's the log of 1,000? Well, log of 1,000 can be rewritten as 10 to the 3, so that's just a log of 10 to the 3, so it's got to be 3. Right? So all we've done here is just rewrite 1,000 in its exponential form, which then allows us to easily take a log of it. But what's the log of 1? It's 0. All right, it's 0. The log of 1 is 0. Okay, now to set the stage to get back to pH, the log of 10 to the negative 7 must be negative 7. Okay, so therefore, pH defined as the negative of the log, well, the negative is here because we want the pH values to all have positive values. It's really the only reason, just to make the scale itself positive, right? So the definition is pH equals negative of the log of the concentration, the molar concentration of hydronium ions, okay? So for acidic water with a pH less than 7, then you might have less hydronium, all right? And in that case, maybe you only have negative 5, all right? So in this case, right, then you take a look at that and you have a pH equal to 5, all right? On the other hand, for basic water, all right, then you have a 10 to the negative 9 value, and you've got a pH value of 9, all right? So then if we look at our concentrations, we see that where we have very high concentrations, so such as here with 10 to the 1, well, that's going to have a pH value that's very, very low, so low it's below 0. On the other hand, when we have concentrations that are pretty high, like only basically there's 1 hydronium ion for every 100 H2O, H2O every 100 water molecules, H2O molecules. Well, in that case, you have something like vinegar, right, which has an acidic or a pH value of 2 because it's quite acidic. On the other hand, as you get tiny amounts of hydronium, as you get up into bases, and your hydronium is minuscule, you only have 10 to the negative 14 in terms of your molar concentration. So you've got less than 1 trillionth of the contents of the mixture or the solution being hydronium. Well, in that case, you have something that's very basic. The example of something that's very basic is oven cleaner. Okay? So very strong bases have dramatic effects. Oven cleaner, hair remover, ammonia. Very strong acids are the same way. All right? Things in the middle tend to be easier to handle biologically speaking. Okay? So acid rain has a pH lower than 5. That comes from it mixing with this sulfur-oxygen mixture, all right? And then the sulfur dioxide is released from burning coal and oil. And also carbon dioxide levels also create this aqueous, that's the AQ stands for, an aqueous mixture that is also acidic. Acidic rain can lead to destruction of stone, including stone artifacts, and can kill forests. What's interesting is acidic rain is pretty manageable in limestone lakes because the limestone releases, so the hydronium ions are neutralized by the carbonate released from the limestone. So the limestone releases carbonate, which neutralizes the hydronium. On the other hand, if the lake is surrounded by granite rock, there's no neutralization happening, and the acidic level just goes up and up until it becomes harmful to the ecosystem. As far as freshwater lakes with a pH that's less than 7, so acidic saltwater lakes, they basically aren't carbon dioxide sinks. They absorb and release equal amounts of carbon dioxide. On the other hand, the ocean is basic, and although it's becoming gradually more acidic, it's still, as a whole, the ocean is basic. Therefore, it is a carbon dioxide absorber. Okay, up to a point. And acid-base reactions transfer a proton. Just to bring it back to the basics, right? We saw the applications to the environment, but big picture, acid-base reactions transfer a proton. On the other hand, there's a different type of reaction, which was presented in the beginning of this chapter, which is oxidation reduction reactions. Well, these ones are a transfer of something else fundamental. It's an electron. Okay, so if acid-base reactions are all about protons moving from one place to another and the creation of ions, oxidation reduction reactions are all about moving of electrons. Now, I'm not going to go into as much depth when I talk about these oxidation reduction reactions, because I do want to wrap up this lecture, but also because we're not going to focus on these as much. We need to understand that they're a counterpoint. They involve the exchanging of electrons and a bit about where we see them. Okay, so oxidation is the loss of an electron. All right, so for example, we have neutral sodium becoming a sodium ion because it gave up electrons. Okay, so it got a net positive charge because it lost electrons. On the other hand, reduction is the gaining of electrons. So for example, chlorine gas can gain electrons and become a negative ion. Okay, so reduction, you gain something, oxidation, you lose it. Now that can be a little confusing because literally when you reduce it, you gain something. And that's not typically how we use the words. But remember, reduction ends with a negative ion and oxidation ends with a positive ion. Okay? All right, and another mnemonic device to help you remember is Leo and Gur, and Leo, the lion, went Gur, all right, because loss of electron for oxidation, so loss electron, oxidation, and then gain electron reduction. Leo, the lion, went Gur. Okay, so here's an example of an oxidation reduction reaction, all right, gaining positive ions and negative ions. All right, now which elements tend to oxidize and which tend to reduce? Well, the elements from the periodic table, because that's what we're showing here, periodic table. The elements that are more likely to behave as oxidizers are the ones in blue. They're the ones that tend to, not behave as oxidizers, behave as reducers. All right, oh no, behave as oxidizers, right? Because they are more likely to behave as oxidizers. Excuse me, really stumbling over my words there, right? So the ones in blue, because they gain electrons, which is to say they behave as oxidizers. On the other hand, the ones over here are more likely to lose electrons, right? Because they're more likely to behave as reducing agents. So we don't call them reducers, we call them reducing agents. So oxidizers or oxidizing agents and reducing agents, okay? So they're more likely to be oxidized, and then these ones over here are more likely to be reduced, okay? Which is to say, if you gain an electron, you're reduced. That's probably the clearest way to say it. Again, all right, over here, you lose an electron, you're oxidized. All right, so if we're looking here, these are going to be things like calcium, all right, for example, is going to fall in this category. Over here, we're going to have things like oxygen. Okay, so oxidation, the ionic state becomes more positive because it lost an electron, it gained an oxygen, and loses a hydrogen. All right. In reduction, the ionic state becomes more negative because it gains an electron, loses an oxygen, and gains a hydrogen. Okay, so what element within the reactants is oxidized in the following equation? And what element is reduced? Okay, so again, this is just coming down to remembering the terms. Which one is oxidized and which one is reduced? Okay, so the reduced one should gain an electron, so then it should become a negative charge. So which one is that? Okay, iodine is reduced because look, the iodine became a negative ion, which means it had to be reduced. Meanwhile, the bromine became a positive ion, which means it was oxidized. Good. Okay, So electric currents generated by oxidation reduction current reactions are quite common, all right? Batteries and fuel cells use this principle. Now, you might think of a potato as being a wonderful example of a biological battery, and it does work, but you need more than just connecting something that produces positive ions and something that produces negative ions, okay? You also need what's called a salt bridge to keep the whole thing flowing and to get those flow of electrons. Because we can see over here that with the oxidation of the iron is losing electrons. Those electrons then can flow through the wire and thus through the resistor, generating light, as long as they can get readily absorbed by the copper in the penny. In this case, this is not a potato, excuse me, the penny. But the copper in the penny is then absorbing the electrons. I thought it was a potato by the shape of it, but we can clearly see here it's a penny, also based on the fact that it's made out of copper, and potatoes are not made out of copper, but pennies are. All right. So anyway, so the copper then is absorbing those electrons, okay, which is of course a reduction process, and that then is going to keep flowing as long as salts that are created as a byproduct of this reaction can then flow from one chamber back to the other to keep things going. Okay, this is the idea behind a battery, right, which is a self-contained voltaic cell. So it's going to use those similar chemical processes to keep flowing of electricity until eventually it's ran out of basically, these easily oxidized or reduced elements on the surface of the materials. Once they've all been turned into salts, then it's ran out of energy. It doesn't go forever. The positive electrode is the cathode, where reduction occurs, and the negative electrode is called the anode, and that's where oxidation occurs. So very, very important terms here. Anode, that's where oxidation occurs. Cathode is where reduction occurs. Okay? So there are several types of batteries: dry cells, alkaline, even rechargeable batteries like lithium. Fuel cells convert the chemical energy of a fuel into electrical energy. Here's an example of that, again involving oxidation and reduction. Okay, oxidation, giving up the electrons; reduction, absorbing them. Right. So clearly, it's very important for these chemical reactions of producing energy. Right. So really important to our modern world. Okay. Furthermore, electrolysis uses electrical energy to produce chemical change. It's basically running the other way. What if you put the flow of electrons in? Can you induce oxidation, right? Can you induce reduction? Absolutely, right? So that's like recharging a battery, purifying metal, right? Those are examples of flowing electrons, so actually inputting electrons in order to force a actual chemical reaction. All right. Also happens within the environment. We can have corrosion, right? So corrosion is the process whereby a metal deteriorates through oxidation reduction reactions. And right, this can be somewhat prevented by having a zinc coating where the zinc oxidizes first, thus reducing the structural damage of the things underneath oxidizing. Okay. Also, combustion is an oxidation reduction reaction between a non-metallic material such as wood, in this case methane, and oxygen. All right. And in this case, we have one playing the role of the oxidizer, the other as the reducing agent, and then we end up with a reaction of combustion. And you notice in combustion, a byproduct of combustion is water. So interesting question, one of the products of combustion is water. Why doesn't this water extinguish the combustion if you're thinking like a campfire? Well, what's the best answer here? It's that the water is in the gaseous phase and just floats away. All right. Well, we're finally done with our big, long double lecture on chemical reactions. A lot to take in, but hopefully it was interesting. Thank you so much for watching.